Welcome. This talk introduces our recent work about parallel routing. I am Minghua Shen from Shen University. In the contents, there are 4 sections. The introduction is presented at first. FPGA is a programmable fabric able to provide a better trade-off in terms of cost, power, and performance compared with the general purpose processors. This is an increasing interest in the large-scale use of FPGAs as application accelerators, especially for data centers. For example, Microsoft uses FPGA to accelerate the Bing search engine. The key advantage of FPGAs is to provide high performance per watt. Mapping an application onto FPGA depends heavily on CAD tools. Routing is one of the most critical stages in the FPGA CAD flow. Routing is used to find a feasible path for each net in the circuit. This is a disjoint path problem and NP complete. To study the routing problem, the routing architecture can be described as a routing resource graph, which is used to explore the routing algorithm. Pathfinder is the representative routing algorithm, which is the basis for most commercial routers such as Shen's Vivado router and the Intel Quartus router. In Pathfinder, the group router is used to route all nets and invokes a single router to route a net. Both group and single routers are performed interactively until finding a feasible routing solution. As the size of FPGA increases, it takes a very long time to find a feasible solution. For example, the Intel Quartus route takes over 24 hours to finish the SHA design. Here, we also provide an example to use the Pathfinder algorithm to route 2 nets. It is a feasible routing solution for 2 nets. There are 2 ways to parallelize the Pathfinder algorithm. One is coarse grain and the other is fine grain. In the coarse grain, we route different nets in parallel. In the fine grain, we parallelize the routing of a single sync subnet on a net. In this work, we focus on coarse grain parallel routing, and we explore the partitioning and parallelization of multiple nets. The major challenge is dependencies between nets due to the inherent routing order. Now the motivation is introduced. The motivation for our parallel router is that the number of terminal pins is different between nets, leading to the load imbalance in the parallel routing process. This problem is demonstrated by 2 experiments as follows. In the first experiment, we studied the impact of different number of pins on the executing time of routing a net in serial routing. In this experiment, we have 2 observations. First, the long net has long execution time in the same interaction. Second, with the increasing number of interactions, the execution time of each net is increasing continuously. Those 2 features impose the load imbalance problem when we perform the parallel routing of multiple nets. In the second experiment, we studied the impact of different net time on the speed up of basic parallel routing. We implemented a basic parallel router consisting of partition, synchronization, and parallelization. In the partition, nets are designed to subsets. In the synchronization, we continue the intermediate routing state to find a feasible solution. In parallelization, we use MPI to program the routing, and the routing time is reduced. In this experiment, the number 4 core has more long nets, taking max time, while the number 6 core has more short nets, taking mean time, both of which result in the load imbalance problem. Notably, the number of parallel routing depends on the time of the number 4 core. In order to solve the load imbalance problem, we present a new parallel router. Now our parallel router is introduced. It consists of static load balance partitioning and dynamic load balance parallelization. In our parallel router, we still maintain the regularization-based Pathfinder framework to find a feasible solution. In the pre-processing, the static load balance partition is performed before parallel routing. In the runtime processing, the dynamic load balance parallelization is performed at runtime. In static load balance partitioning, we consider regular and irregular region partitioning methods. In the regular region partitioning method, the size of each subregion is same, and the number of nets in the set is different. In the irregular region partitioning, we impose a load balance metric, the number of nodes visited in the previous interactions, which is used in previous works, such as FPT-TCAD. In this way, the size of subregion is different, and the number of nets in the set is almost the same. This ensures the load balance between cores before parallel routing. In dynamic load balance parallelization, we perform the basic parallel routing with load balance at runtime. Further, the routing task is migrated between underloaded and overloaded cores. This example is parallel routing based on regular region partition. The master MPI process P0 routes. Loads the nets or read set and then combine with the slaver MPI process P1 to parallel route the nets or the remaining two sets. The partitioning can be recursively performed. We also show the task migration between cores when adopting 8 cores. This ensures the load balance between cores at runtime. At last, the evaluation and the congestion are introduced. We implemented the proposed parallel router in the latest VTR8 CAD framework, which is performed on 4 CPUs running at 32 GB memory. In our experiments, the baseline is VTR8 serial route, and the channel width is set to 300 by default. The parallel router is basic parallel routing based on load balance partition. On average, our parallel route achieves about 13 speed up with 32 cores compared with VTR8 serial router. The parallel route plus is load balance parallel routing based on load balance partitioning. On average, our parallel route plus achieves about 17 speed up with 32 cores compared with the VTR8 serial router. With the number of cores increases, our parallel plus has an increasing impact on the quality. This is because our parallel plus changes the original routing order in the partitioning and parallel routing processes. In addition, our parallel plus provided repeatable parallel routing results, although it is not serial equivalent. Finally, we show the runtime breakdown. Our parallel plus with 32 cores averaged over the 50 pattern designs, and the runtime breakdown of the parallel routing part in our parallel plus is shown in the figure B. At last, we give the conclusions. We propose a load balance-centric distributed parallel route for large-scale FPGAs. We explore regular and irregular region partitioning for static load balance before parallel routing. We migrate the routing task between underloaded and overloaded cores for dynamic load balance at parallel routing time. Our parallel route scales up to 32 cores to provide about 17 speed up on average compared with VTR8 serial router. Okay, thanks. Questions?